As capable structural engineers, we would like to design capable structures. But what do we mean by capable, and what limits this capability? By capability, we refer to the ability of a structure to fulfill its function to carry and transmit loads. We have seen the various loads carried by different aircraft structural parts already, but how could this function be disrupted? The obvious answer is that if a structure breaks, it can no longer fulfill its function. It loses its capability. Perhaps a little less obvious, however, is that excessive deformation can also prevent a structure from fulfilling its function. We can illustrate this with a simple thought experiment. Imagine we built a very flexible bridge crossing a river. While walking across this bridge, it begins to deform until it touches the bottom of the river once you reach the middle of the bridge. Not the most useful bridge ever built, but it does illustrate the point that excessive deformation can influence the capability of a structure, even if it does not break. As engineers, we can control these influences on capability through our design decisions. Both the material and geometry we choose for a structure will influence when it will break and how it will deform. This leads us to the question of why don't we just use the strongest and stiffest materials and structural geometries? This question is often brought up in the context of one of these, a flight data recorder, which, despite not being black, is often referred to as the black box. This recorder is designed to protect valuable flight data in case of a serious accident. It is effectively designed to survive an aircraft crash. So why don't we simply design and build the entire aircraft just like the flight data recorder? Why can't we make the entire aircraft equally indestructible? The reality is that an aircraft is not simply a structure. It's a complex system that has other constraints which limit its capability. If the aircraft weighs too much, it might not be able to take off. If it costs too much, it might be too expensive to operate and less people would be able to afford to fly. Or, if it does not have the right aerodynamic shape, more and more fuel might need to be burned to get it to fly. So we have to make some decisions. We have to trade off structural capability in order to fit within the design constraints such as weight and cost. In essence, all engineering structures, including aircraft and spacecraft, are a compromise. More than that, there are many possible solutions that will meet the structural capabilities. I could choose just about any engineering material and develop a design that could work with that material choice. So how do we come up with the right solution for a given problem? In essence, we have to justify our decision in terms of the design constraints. Luckily for us, in the aerospace industry, typically weight is the most important design constraint. We typically optimize for the most weight-efficient design. However, in a growing competitive aerospace market, cost cannot be entirely ignored, and sometimes decisions to save cost that result in an increase in weight are made. In the coming week, we will examine this decision process a little more closely and look at some basic ways to compare different design options in order to make sound decisions on the materials and structural geometries to use in our designs.